Okay, so hi everyone. In this flipped classroom video, we're going to go ahead and talk about something called standard electron configuration. Okay, so standard electron configuration is kind of like orbital diagrams. It's just an easier way to write it without having to draw all those boxes and arrows. So the one way that we get started with this is by dividing the periodic table up into what we call blocks, okay? So we have the S block, which is the first two columns. The transition metals are the D block. The last six columns are the P block, except for helium, and then the lanthanides and actinides are the F block. So with this, the period number tells us the energy level that we are in. Except note, the D block we subtract 1, and the F block we need to subtract 2 to get the energy level. And then the column within the sublevel block tells us the number of electrons in the sublevel, which would be like the arrows in orbital diagrams. Okay, so let's work through an example. We're going to do hydrogen first, the very first element. Okay, it was in the first period, in the S block, and it's the first column in the S block. So if we put all that information together, we have 1S1. Okay, so 1 in the beginning, that's the period, S block, and notice that's lowercase s, and then the superscript is the column within the S block. Okay, so let's go ahead and try another one. The next one is cobalt, which is a transition metal. It's found right there. So if we look at this, cobalt is in the fourth period, in the D block, and if we count across, it is the seventh column in the D block. So for cobalt, we would have 3d7. Remember, we subtract 1 when it's in the D block, so instead of being 4d, it's 3d, and then the 7 again is that column number. Okay, the next one is thorium. Okay, so thorium is all the way down in the F block. So it's in the seventh period, F block, and it is in the second column. So if we put all of that together, we end up with 5F2. Remember, for the F block, we subtract 2 from the period number, so that's why we have 5 and not 7. And then it's in the second column. Okay. So using the periodic table blocks, I want you to go ahead and describe the location of the following elements. So go ahead, pause the video, figure these out, and then once you have your answers, come back and we'll show them in a second. Okay, so let's go through the answers. So beryllium is 2s2, argon is 3p6, silver is 4d10. Remember to subtract 1 from that period number. Uranium is 5f4, so remember to subtract 2 because it's in the F block. And then chlorine is 3p5. Okay, so this describes the location of an element, but it doesn't tell us where all the electrons are located, so we need to provide more information. So standard electron configuration is what's actually going to tell us the location of all of the electrons in an atom. Okay, and due to the Aufbau principle, that tells us we need to fill the lower energy orbitals first, we start with the lower ones and we work our way up to the higher energy orbitals. So, because oxygen's position is 2p4, we need to completely fill the orbitals that come before it, which happen to be the 1s in that first period, and then the 2s is in the same period, but it's to the left. So whenever you're figuring out which order to go in, remember, work top, left, to the right, and then move down to the next row, left to right, always working your way down, just like you read a page. Okay, so the first thing you want to do is figure out the total number of electrons in an atom and write in the standard electron configuration. You're then going to determine the location of the atom, just like we did before. Okay, then we're going to fill up all the lower level energy subshells to their maximum capacity. Remember, the s orbital can hold a maximum of 2, the p orbital can hold a maximum of 6, d is a max of 10, and f is a maximum of 14. We're then going to write that final orbital that describes the location of the atom, so in this case 2p4 for oxygen. And then we're going to check our work. Does the total number of electrons equal the superscripts? So if we look at this for oxygen, we have 2 plus 2 plus 4. Well, that's 8, which is the atomic number for oxygen. So we are good. Okay, so as I mentioned, orbital diagrams and electron configurations are really related. They both follow the same 3 orbital filling rules, so Pauli exclusion principle, Hund's rule, and also the Aufbau principle. Also, the superscripts in the electron configuration are the same as the number of arrows in the groups of boxes. And then the orbitals also come in the same order for both the orbital diagrams and the electron configuration. So remember, we always had a single box, and then a triple box for orbital diagrams. Well, in this case, we have 1s, 2s, and then 2p. So they all kind of get tied together and are describing the same thing. It's just different ways of doing it. Okay, so electron configurations for very large atoms. First off, I want to point out that lutetium and lawrencium are actually part of the D block. Even though they're kind of grouped down with the lanthanides and actinides, they are considered part of the D block. And then also for periods 6 and 7, the orbital that we're going to fill those the order we're going to fill the orbitals is the S, followed by the F, and then the D, and then P finally. So let's go ahead and actually try out some examples with this. Okay, so for this next part, I want to go ahead and actually write out the electron configurations for 2 really large atoms by hand so you can see how it all fits together. Now, don't panic. I know that this is a lot, but I'm never really going to ask you to do these super huge atoms, so just take a breath, it'll be okay. But we're going to go ahead and do it together so you can kind of see how all these pieces fit together. Now, I already have my periodic table set up here with my different blocks. So I have my S block, my D block, my P block, and my F block. And I've also listed the number of electrons I can have in each of them. So I can have 2 in the S block because I have 2 columns, 6 in the P block because I have 6 columns, 10 in the D block because I have 10 columns, and then 14 in the F block. Remember that lutetium and lawrencium, they're actually part of the D block right here, so they only get counted for 14 columns. So let's go ahead and get started with this, okay? So we always begin with the very, very first row. So this is the 1s block, and we can fit 2 electrons in it. Until we get to our very last orbital, we're going to fill all of them up completely. So just know we're going to do the maximum whenever possible. So 1s2. The next one is going to be the 2s2. Remember, we read left to right, and then we move down the next row once we've finished up a row. So 2s2. And then here we have 2p6. Moving on down, we have 3s2 and then 3p6. Next row, this is going to be the 4th period. So this is going to be 4s2. And then remember, for the D block, we subtract 1 from the period number. So instead of being 4D, we're going to have 3D first. So 3D10. And then the P block goes right back up to that 4. So we're going to have 4P6. Next, move on down. We have 5S2. And then we have our D block. Remember, subtract 1 again. So we have 4D10 and then 5P6. Moving on down. Okay, so we have, let's fill in our periods. We're now up to 6s2, and then this is where the F block is going to come in, okay? So now we're going to move on down here, and we want to go to cerium, which is right here. So this is actually period 6, but we're going to subtract 2 because we're in the F block. So instead of being 6F, is actually going to be 4F. And then we're just going to end right there because it's the second one, so 4F2. So that is the electron configuration for cerium. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Remember, subtract that one number. Okay, but then it bounces right back up for the next one. Okay, and then 5s2, 4d10, 5p6, and then 6s2, and then we go to the 4f block. Okay, so that is the electron configuration for cerium. So now let's go ahead and do francium. Okay, so again, we start at the very, very top and we work our way down. So we have 1s2, and then 2s2 and 2p6. Next, we have 3s2 and 3p6. Okay, and then we have the 4s2, remember 3d10, and then 4p6. Next, we have the 5s2, 4d10, and then 5p6. And then we get to the sixth period, so we do 6s2. Remember, we jump down to the F block. Okay, now in this case, we want to go all the way across the F block, so we're going to have 4f14. And then after the F block, we're going to jump back to the D block. Okay, so remember, we still subtract 1, so instead of being 6, we're going to have 5. We're going all the way across, so it's going to be 5d10. And then we finish up with 6p6 for this period. So to reiterate, we start with a 6. We subtract 2 for the F blocks. That's where that 4 comes from. We only subtract 1 for the D block, so that's why it's a bigger number. And then we go back to where we started from. Okay, so that's a 6p6. And then we're going to finish up with period 7. This is the S block, and then it's the very first one. So 7s1. Okay, so those are the two electron configurations for those very large atoms. I hope this helps, and stay tuned for the condensed electron configuration.